My name is Youngin Choi, and I'm a PhD student in Dr. Gerald Cohen's lab at UC Davis. I'll be presenting our work siVAE, a scalable and interpretable VAE. VAEs are one of the most widely used generative models used for dimensionality reduction that infers lower dimensional embeddings of samples. While VAEs are more powerful than their linear counterparts, such as factor analysis and principal component analysis, one major drawback of VAEs is their interpretability. To be precise, canonical VAs do not output the contributions of each of the input features towards each of the latent dimensions learned during training, as these contributions are implicit in the model parameters. This is in contrast to factor analysis and principal component analysis, which directly outputs these information in the form of factor loadings. Here, we propose the scalable interpretable VAE siVAE model, a variant of VAEs that simultaneously infers a loading matrix to describe feature contributions to latent dimensions, while being comparable in training time and power to a standard VAE. siVAE is a Bayesian extension of VAE that learns prior on the last layer of weights in decoder, where the prior samples a feature embeddings that acts as a loading matrix. The key intuition of siVAE is that the feature embedding interprets the sample embeddings. In order to do so, the dimensions of the feature embeddings need to correspond to those of the sample embeddings. And to encourage correspondence, we add an interpretability regularization term to the VAE loss function. Typically, the loss function for VAE consists of the KL divergence term and reconstructionless term, which are shown on the top line. The added regularization term encourages the individual latent dimensions of sample embedding and feature embedding to correspond to each other by encouraging the linear product between the two to approximate the input data X. Interpretability can be enforced in every layer of the decoders, or just the innermost layer. The principal benefit of our model is siVAE feature embeddings that form a factor loading matrix analogous to PCA factor loadings. They can be used to quantitatively measure feature contributions to sample latent dimensions, or in other words, interpret latent dimensions with respect to features. With imaging datasets, for example, this allows visualization of individual latent dimensions. Here, we apply siVAE to MNIST and visualize 4 out of 20 inferred latent dimensions, and visually verify that the latent dimensions capture the outlines of different digits. In addition, we compare our results against traditional feature attribution methods, which can be applied to either decoder or encoder to produce a factor loading analogous to siVAE loadings. We see that while feature attributions on the encoder is inconsistent with siVAE loadings, decoder attributions produces loadings comparable to the siVAE loadings. However, most feature attribution methods were designed for networks with small number outputs, and do not scale well to decoders that output same number of input features. In a runtime experiment, we found that siVAE is at least 2 times faster than traditional feature attribution methods. In addition, we verified that siVAE dimensionality reduction performance is comparable to VAE through testing classification accuracy of latent embeddings. Finally, we introduced feature awareness that captures which feature each layer of siVAE model focuses on reconstructing well, and it does so by measuring the improvement in the model reconstruction loss over the baseline reconstruction loss. In general, we see that the inner layers of decoder, where L equals 1, are aware of the broad outlines of the objects, while later layers, where L equals 3, capture more finer details. To recap, siVAE learns feature embeddings that guide the interpretation of sample embeddings at least twice as fast as it would take for traditional feature attribution methods. In addition, the interpretability term could be used in conjunction with other variants of VAEs. Thank you for listening, and please take a look at the paper for further details.